Hello, so today we will be talking about radioactivity and nuclear equations. Our learning target are as follows. You can define and describe radioactivity. You can express the changes in the atomic number and mass number of a radioactive nuclei when alpha, beta, or gamma particle is emitted. And lastly, you can write nuclear equations for alpha and beta decay reactions. By the way, this is Sir Anton and you can call me Sir A for short. A legendary chapter in physics began with the discovery of the phenomenon known as radioactivity. Radioactivity is an integral part of the environment, and it was not invented but was discovered in the late 19th century. It was pioneered by a French physicist and engineer, Henri Becquerel, in 1896. He found out that this uranium compound, when placed near a photographic plate, made an image on the plate even if the compound was wrapped in a black cloth. He reasoned out that this uranium compound was emitting some kind of emission that passed through the cloth to expose the photographic plate. Now, these emanations were called as radioactivity. Alongside Henri Becquerel, there are also other scientists who made a milestone in the study of radioactivity. So, first, we have Wilhelm Röntgen, who discovered the X-ray in 1895. In doing so, he actually paved the way for the discovery of this natural phenomenon. And it was not Henri Becquerel who coined the term radioactivity. Instead, it was the Curies with their discovery on radium and polonium. In addition, we also have this ever-famous scientist in the person of Ernest Rutherford, who studied the most common types of radiation, the alpha and beta radiation. So that is Wilhelm Röntgen and Henri Becquerel. So let's take a look at the review on an atom. So let's have a quick review. We all know that an atom is composed of three subatomic particles, namely the proton, electron, and neutron. And collectively, protons and neutrons are known as nucleons. So it constitutes the atomic nuclei in an atom. And this also paves the way for the differentiation of different elements. So we have the different nuclear species. As you can see here, there is an atomic symbol, and there are 118 atomic symbols that would represent different atoms in chemical formulas. So the A number there would represent the mass number, the number of protons and neutrons in an atom. And of course, the Z number, that is referring to the number of protons in an atom. In our example, we have here carbon 12. So the 12 there would represent the number of protons and neutrons. That's 6 plus 6, and that is equal to 12. Now, so one or two species of atoms of a chemical element with similar characteristics is referred to as an isotopes of a particular element. Remember that every chemical element has one or more isotopes with the same atomic number and position in the periodic table and nearly identical chemical behavior but with different atomic masses. As you can see here in our examples, we have carbon 12, 13, and 14. For carbon 12, there are 6 neutrons and 6 protons. For carbon 13, there are 7 neutrons respectively and 6 protons. That means there is an extra proton. And for carbon 14, there are 2 extra neutrons. Okay? So we need to remember that all of these elements, that all of these atoms rather, seek for stable configuration. As they seek for stable configuration, they turn into different nucleus. All nuclei with 84 or more protons are radioactive, and elements with less than 84 protons have both stable and unstable isotopes. All of these elements can go through nuclear changes and turn into different elements. The nuclei of most atoms are stable. However, certain atoms have unstable nuclei due to an excess of either protons or neutrons or an excess of both. Here, in our periodic table, most of the radioactive elements can be found in the period number 7. And here, that includes the actinide series. And as an exemption, 43 here, the atomic number of technetium is also radioactive, but it is an exemption. So let's take a look at the exercises. All elements with Z number is greater than 83R. Z there would pertain to the atomic number. So A, stable and unreactive. B, radioactive. C, likely to decay by alpha emission. D, likely to have neutron or proton rations of less than or equal to 1 is to 1. And the correct answer actually is letter B, radioactive. Okay, so that is just a learning check. Now, the nuclei of a radioactive atom change spontaneously into another atomic nuclei, which may or may not be radioactive. They are described as radioactive and are known as radionuclides or radioisotopes. So the process, the irreversible transformation of radioactive atom into different type of atom is known as nuclear transmutation or nuclear disintegration. It is accompanied by different types of emissions of radiation. A chemical element can therefore have both radioactive or radioactive nuclei. Here, the unstable nuclide is called as the parent nuclide. The nuclide that results from the decay is known as the daughter nuclide. Here in our picture, the parent nuclide, which is unstable, is subjected to radiation that in the process becomes stable, and the unstable daughter nuclei, which may be stable or unstable, becomes stable eventually through the process of disintegration or nuclear transmutations. The rate of radioactive isotope decays will be discussed later on. But take a look at this. There are two types of radioactivity. We have the natural and artificial radioactivity, and obviously they have difference. Here, in the process of natural radioactivity, it is spontaneous, but in the artificial radioactivity, it occurs in the presence of external force or influence. In addition, the initial material for natural radioactivity is unstable, and for the artificial radioactivity, it's stable. And of course, they have different controls. For the radioactivity, natural radioactivity, it cannot be controlled as it continues to disintegrate to achieve the stable state. And for the artificial radioactivity, basically the process can be controlled. As mentioned earlier, the rate at which a radioactive isotope decays is measured in terms of the rate of radioactive decay of an isotope is measured in half-life. The term half-life is defined as the time it takes for one half of the atoms of a radioactive material to disintegrate. So there are various half-lives for various radioisotopes or radionuclides that can range from a few microseconds to billions of years. Here, in our illustration, the initial amount is 100%. So after the first half-life, what remains is just 50% from the original sample of 100%. So it continues to decrease by by half as time passes by. So each radioactive nuclei has a characteristic. So there is a constant half-life for each of the radionuclides or radioisotopes. So there is this time required for half of the atoms in a sample to decay. Here, each of the isotopes half-life allows us to determine how long a sample of a useful isotope will be available and how long a sample of an undesirable or dangerous isotope must be stored before it decays to a low enough radiation level that is no longer a problem. So it basically helps us to determine whether a particular substance is still radioactive or if it reached its stable state already. So let's have a learning check. So half-life is A, constantly changing, B, half of lifetime of an unstable nucleus, C, the time for one half of unstable nuclei to decay, or letter D, independent of the rate constant for decay. So what do you think is the answer? The correct answer is letter C. So a half-life is the time for one half of an unstable nuclei to decay. Remember, there is this term unstable nuclei. So the time there basically is the element, the independent element that we are after too. So the amount of the substance would depend upon the time or the half-life of a particular nuclei. Let's take a look at the sample problems. The half-life of zinc-71 is 2.4 minutes. That means it decays by half in 2.4 minutes. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes has elapsed? So what we are actually looking for is the amount that has remained after 7.2 minutes. So first, in answering this question, we need to determine the number of half-lives that have passed. So the formula for this is the number of half-lives is equal to the time passed divided by the half-life. So since the number that have or time passed is 7.2, we need to divide this by 2.4 and that is equal to 3 half-lives. So that means that it divided by half 3 times. So 1 half times 3 is equal to 0.125. This is the amount remaining after the 3 half-lives. Then, by getting this amount, we need to multiply this to the total number of mass at the beginning of its decay. So that is 100 grams. So 100 times 0.125, it would give us 12.5 grams of zinc 71 after 7.2 minutes. So we can also use the isotope remaining equation to solve for how much isotope will remain after the number of half-lives was determined in our first solution or in our first step. So the answer is 12.5 grams. For sample problem number 2, it's very easy. So fermium-253 has a half-life of 0.334 seconds. That means it decays after that's a very minute amount of time. A radioactive sample is considered to be completely decayed after 10 half-lives. How much time will elapse for this sample to be considered gone? Okay, so it's very easy. We just have to multiply the amount or the half-life of that particular atom of or element or isotopes to 10 because it will decay after 10 half lives before it is considered gone. So 0.334 times 10 would give us 3.34 seconds. That means this particular isotope will be gone after 3.34 seconds. That fast, huh? So that is for the sample problems in half-life. Decay. Nuclear decay is the process by which an atomic nucleus emits particles or electromagnetic radiation. This is synonymous with nuclear transmutation and nuclear decay. Here, in this picture, it represents the uranium-238 decay chain series by which as the uranium disintegrates, it releases this particular particles and radiation. So it is represented by Greek letters, and we will be talking about more of this later. Now, radioactive decay is basically expressed through nuclear equations. Nuclear equations represent the reactants and products in radioactive decay, nuclear fission, or even in nuclear fission. Instead of chemical equation where it shows a different number of elements, it is conserved in a reaction. In nuclear reaction, the atomic mass and proton number are conserved. In this case, a balanced nuclear equation is one where the sum of the mass numbers that is situated at the top here, the 238 and the 234 on the other side for thorium, and the helium, which is 4. They should be equal. And of course, the sum of the atomic numbers should also be balanced on the either side of the equation. So here, in this case, for uranium, we have 92, thorium 90, and helium 2. So it should be balanced. So 234 here, 234 plus 4 of helium would result to 238, and 2 for helium and 90 for thorium would result to 92. But in this process, we are talking about radioactive decay. So the uranium here basically will disintegrate to form a more stable atom or nuclei in the form of thorium and helium. Now, here. So we need to take into consideration that nuclear equation should have a balanced number of reactants and the products. Okay, so the mass numbers of the products and the mass numbers of the reactants should be equal. And of course, the sum of the charges of the reactants equals the sum of the charges of the products. So this is just like balancing the equation. So the only thing there is that we are looking into the mass numbers or the atomic numbers and the charges on both sides of the equation. It might either be in the product or reactant side. It should be balanced. Radioactive decay has three types, three commons of radioactive decay. We have the alpha, beta, and gamma decay. And each of these radioactive decay basically emits a certain particle or radiation. Let's discuss first alpha decay reactions. So, an alpha decay emits an alpha particle. It is symbolized by a Greek letter, alpha, and an alpha particle is composed of two protons and two neutrons and is the same as the helium nucleus. Here, in alpha decay reaction, the mass number changes or is decreased by 4, and the atomic number is decreased by 2. Again, mass number is decreased by 4, and the atomic number is decreased by 2. This is just the same as the helium 4 nucleus. So this is the general formula for the alpha decay. In this general formula, we can see that there is an elemental symbol here on the left hand side of the equation. This represents the parent nuclide. This is the daughter nuclide, and this would represent the helium atom or the alpha particle. In this illustration, it is very clear that the parent disintegrates, and it results to a more stable daughter nuclide, and thus emitting an alpha particle. So remember that the number or the mass number should change or should be decreased by 4, and the atomic number should be decreased by 2. So that is an alpha particle. But let's take a look at the example. Here, in our first example, uranium-235 yields into, okay, helium and thorium. So the uranium disintegrates into a more stable element, thorium. So here, since uranium has a mass number of 235 and thus emitting an alpha particle which has 4, a mass number, and 2 for the atomic number. So 235 minus 4 should be equal to 231, and 92 minus 2 would be equal to 90. And the 90th element that can be found in the periodic table is thorium. So that is just very simple. You just have to consider that both of the equations is balanced. So another example here, thorium 230 basically emitted an alpha particle. Okay, so that's 230 minus 4, and it would give us 226. On the other hand, for the atomic number, 90 minus 2 would give us 88. And the 88th element in the periodic table is radium. And this is radium-226. This is a specific isotope of radium. So let's see if the equation is balanced. 230 minus 4 would give us 226. 90 minus 2 would give us 88. Here in our last example, here, radium-222, okay, has an atomic number of 88, emitted an alpha particle. Here, it's an alpha particle. So that's 222 minus 4 would give us 218, and it has an atomic number of 88. Minus 2 would give us 86. So this is a specific isotope of radon. So that's, since it is the 86th element in the periodic table, so it gives rise to a more stable nucleus radon. Again, you just have to be very careful to balance things out. So 218 plus 4 would give us 2224 radium. Let's take a look at the learning check. Okay, here, first question. An alpha emission is associated with A, conversion of neutron to a proton, B, conversion of a proton to a neutron of rays, C, increase in mass number, D, decrease in mass number by 4 and atomic number by 2, and E, emission of gamma rays. So obviously our answer would be, of course, letter D, because alpha emission is associated with a decrease in mass number by 4 and atomic number by 2. Here's another example. The isotope of titanium 48 is produced by the alpha decay of which of the following? So we need to take into consideration that this titanium 48 is already the product. When I speak of the product, it is on the opposite side of the equation, and it is with the alpha particle. We all know that the alpha particle has 4 uh, mass number and 2 for the atomic number. So since this is an isotope and it's a 48, it's just right to say that this is a mass number. Should we add 2 or 4 to the mass number? The correct answer is that we should add 4 for the mass number. So that's 48 plus 4 would give us 52. And the nearest answer would be letter C. That's chromium 52. So that is an alpha decay. Type of a radioactive decay is what we call the beta decay, and this type of decay emits a beta particle. So this is the second type of radioactive emission and is symbolized by a Greek letter beta. So a beta particle is an electron ejected from the nucleus and has a charge of negative 1. In this case, the beta decay changes the atomic number by 1, but the mass number remains unchanged. Unlike in alpha decay, wherein it changes the mass number by 4 and atomic number by 2, the beta decay only changes the atomic number by 1 and the mass number remains unchanged, because the beta particle is just like an electron. An electron technically has a negligible mass. So in this case, in the general formula, the parent disintegrates into a daughter nuclei and emits a beta particle. So a beta particle is also synonymous or the same as the electron. So let's take a look at some of the examples. So we have here the uranium. Basically disintegrates to form another element. As you can see, the mass didn't change, but the atomic number changed, that results into a new element. Take a look at the second example. This is carbon 14 with an atomic number of 6. As you can see, it disintegrates into nitrogen. The mass number remains unchanged, but the atomic number changed. So from 6 to 7. Why is this 7? Because the electron is negative. That means there has been a loss, or rather a gain of an electron in this part of the equation. So 7 minus 1, that would give us 6. Another example here, lithium 8 has an atomic mass of 3. It yields into beryllium, which has an atomic number of 4. Since the charge of an electron is negative, okay, so there has been a gain of an electron in this part of the equation. So that's 4 minus 1, so that is equal to 3. But the mass number remains unchanged. Okay, so let's have a learning particle. Here, Beta emission is associated with a conversion of proton, or rather neutron to a proton, conversion of a proton to a neutron, C, increase in mass number, D, decrease in mass number by 4 and atomic number by 2, or emission of gamma rays. So the nearest answer here would be letter A, conversion of a neutron to a proton, since the mass number is not affected, but rather the atomic number is the one that is being affected. So the best answer is letter A. Here, for example number 2, cobalt 56 decays by emitting a beta emission. What is the product? So cobalt 56 emits this beta particle. We all know that the mass number is not affected, but it's just the atomic number. So if it has emitted some kind of radiation, so the best answer here would be letter C. That is nickel 56. Okay, so technically you just have to move one step, no, ahead in the periodic table. So that is our examples for, or rather learning check for our beta decay reactions. Now, the last type of decay is what we call the gamma decay reaction. So in gamma emission, it is symbolized or is represented by the Greek letter gamma. Now, here, pure energy is released, okay? And it will not change the structure of nucleus in any way. That means it wouldn't affect the mass number nor the atomic number of a particular element, but it'll just affect probably the stability of a particular atom. Let's say, for example, if the atom is in an excited stage going to a ground stage or level. So basically, it really wouldn't affect anything in gamma emission. So this is the general formula. So that's 0 for atomic number and 0 for the mass number. So the parent nuclear or nuclide is practically excited and it released this gamma rays. So the daughter nuclei is now in a ground state. Okay, so from excited it went into a ground state and it has released this gamma particle. Let's take a look at some of the examples. Here, as you can see, uranium-35 from its excited stage, it emitted this radiation. So it never changed anything in the atomic mass or mass number of the uranium. Instead, it's just the same. Same as true with technetium. Here, the M here for technetium would represent its metastable. That means it is in its excited stage going to a ground state. So here, an alpha or rather a gamma ray is emitted. Another example is this barium 137. So it just released a photon, in the form of a ray, in the form of gamma emission. So that's it for gamma emission. So we have alpha, beta, and decay radioactive emissions. Alpha, beta, and gamma emissions emissions have different abilities to penetrate matter. Alpha particles is easily stopped by a matter, by a piece of paper probably. Beta particles penetrate slightly into the matter, perhaps a few centimeters at most, and gamma rays can penetrate deeply into the matter and can impart a large amount of energy into the surrounding matter. Now, penetrating power of radiation is inversely proportional with the ionizing power. That means the alpha particle, which has the lowest penetrating power, has the highest ionizing power. So what really is ionizing power? This is the ability of radiation to damage molecules and is analyzed uh, in terms of ionizing power. So when a radiation particle interacts with atoms, this interaction can cause atoms to lose electrons and thus become ionized. So since alpha particles have the greatest mass, it is also said that it has the highest ionizing power, followed by beta particle, which is much smaller than alpha particles, and therefore they have much less ionizing power as compared to alpha particle. Lastly, the gamma rays are not really particles but high energy of form of electromagnetic radiation, and technically gamma rays can pass all the way through thin sheets or thick layers without striking anything, and thus considered to have the least ionizing power. So let's take a look at the summary here. For alpha, the penetrating power is very low, but the ionizing power is very high. For beta, both are intermediate, and for gamma, the penetrating power is very high, and the ionizing power for gamma radiation is very low. So technically, this is the summary for the penetrating and ionizing power of radiation. So let's delve now into our so now let's move on to the brain gauge. So you need to answer this independently, and I'm just going to give you roughly around 5 seconds to answer each of the question. If you need more time, you may pause this video and answer. Okay, number 2. I will be posting the answers for this brain gauge in my next video lesson. Thank you so much for listening. Again, this is Sir Anton.